know about MATLAB, and do you have MATLAB?
I know about MATLAB, but I don't have MATLAB currently in this computer.
Okay. Um, okay.
But
So
yes, I think in Octave you don't have that much support with the libraries. So for doing SDPs and quantum stuff, I think Octave is not enough sometimes because there is not that much support
yes.
for it.
Yeah, I have run that program, seesaw.m, but it is showing some error that SDP var is not defined.
That means Yalmith is not added to the path.
Also, can we run in Mathematica?
You can do in whatever language. It's a concept. It's an abstract concept, and just like operators are not matrices, abstract codes are not like MATLAB codes. Please feel free to use language. I prefer Python myself. It can all be done in Python. That's it's with CBX software. All right. So if there is nobody who has MATLAB ready but not the software is required for the tutorial, I will proceed with the theoretical part. Please tell me now or remain silent up till now if you that you have MATLAB but you do not have the packages installed. So I will show you how to install the packages. If there is nobody like this, we will start the lecture. All right. I think I'm ready to proceed. Okay. Okay. Last time we looked at what can we say for just a second. Um, how SDPs are useful when it comes to characterizing and bounding the set of quantum correlations in Bell scenarios. So specifically, we showed that how SDPs can be used to obtain maximal quantum violations of Bell inequality and how easy it is to code there. I gave an assignment uh, in the tutorial. So if anybody has found the answer and the code, please share it with me. I'll be happy to check it. If there are problems, I'll address it. Anubhav, I was actually trying to do it. Yes. So, using the Q1, the NP hierarchy, I have found the optimal value 0.85, but I think there is some mistake. It should be around 0.70, right? No, no, no. 0.70 is the coefficient when you mix PR box with white noise. Yeah. But 0.85 is the coefficient when you mix PR with PR dash. If what are you mixing? PR with PR dash or PR with white? PR with PR dash. Then it's not 0.767. I have to check whether it's 0.85. But if you can write me an email with the code, I'll make sure. But especially Ram, today might be interesting for you and Samrat if he's here because I'll be focusing on 2 to 1 parity oblivious racks and we introduced a generalized version of them. So these things can be applied to those as a small future or a practice in STP. Nevertheless, okay, this is great. Thanks. I really like that you tried out the assignment and found out the answer. And if you need help with the code, you can always hit me up. Okay. All right. Thank you, Ram. This is like at least somebody has attempted, and I'm sure that you have a proper answer. So just like SDPs help out in finding out what correlations we can get in the Bell scenarios, which is the hierarchy by Miguel Navasquez, Pilonio, and Lassen. Uh, we with Vicky and Mate, we tried to figure out SDP hierarchy to bound a set of contextual behaviors and specifically generalized contextual behavior. Okay, some of you might have heard the theoretical. side of this before when I took a seminar in ICT, but I will go fast with this so that we can jump to the coding session at the end. So we set out, and this was actually started as a bigger program with Devada, and then I did the SDP part for it. So we thought that these are generalized non-contextuality is closely related to Bell's local causality, and non-locality is closely related to contextuality. So the same structure should, or same abstract structure should apply there. Just like you have the no signaling polytope, you can have something like the contextual polytope in generalized non-contextuality scenarios, and the quantum set is both quantum set of probability distributions in contextuality experiment is convex, just like the convex set of quantum correlations in Bell stuff, and the classical set in both cases forms a polytope with finite convex polytope with finite number of extremal points, non-contextual polytope and the local real polytope. Then we thought that, oh, if this is so, then there must be an hierarchy akin to NPA hierarchy, which would bound quantum violations of non-contextuality inequalities, um, and in effect somehow characterize the set of quantum contextual correlations. So during the last burst of pandemic in I think 2020, I set out. Oh no, 2019. I set out because I had nothing to do. I was on my own. I set out writing the code base for such an hierarchy. The hierarchy was discovered like 3 years ago, but I did not generalize it. I finally had the time so that I can do it, and we wrote a paper on it, and this paper is now published in Quantum Journal. Let me check if this is the correct presentation. Maybe just give me 1 second. Yep, now I have the correct one. Nevertheless, I'll send the slide to whoever is interested at the end. So, as I said, this work is now being published in Quantum, and because I was giving this to I was giving this talk to foundational people, I had to make sure that they do not resist my conclusion, which follow from discussions with table at the end. But so for the theoretical side, let's have a Bowman diagram. The theoretical side is will give you the main idea for the design of the hierarchy, and the hierarchy is super easy to implement, and we will retrieve some non-trivial quantum values at the end of this lecture. Anyways, before we talk about generalized non-contextuality, we must talk about the Leibniz law. Okay, Leibniz law. Uh, Leibniz was a very cool dude. He was competing with Isaac Newton back then, and they sometimes I think Leibniz was overshadowed by Isaac Newton in many cases, but he was a mathematician of the highest order and a logician. So, anyways, Leibniz gave a law for all formal theories. So, it is beyond physical theories, it's for all formal theories. It is about the compactness or correctness of a theory. The Leibniz law has two parts: identity of indiscernibles and the indiscernibility of identities. So, identity of indiscernible means that if you cannot distinguish two objects, say x and y, uh, based on any of the properties of x and y, so they have shared properties f, then up to all relevant purposes, these two objects are identical. On the other hand, if two objects are indiscernible, well, this is identity of indiscernible. So if two objects are identical, then they are clearly indiscernible. For instance, you can think of you and you. So you and you are just the same object in the same say space time location. clearly nobody can tell the difference between you and you just because you are you. However, the other side, it's commonly believed that contextuality implies that identity of indiscernibles. Quantum theory violates identity of indiscernibles, which is contextuality, but it is not so. As one can see at the bottom of the slide, in quantum theory, if
I think you are not sharing the slides. You,
oh,
yeah,
okay, it's not okay. Oh, thanks.
yeah.
It says can't share your screen. Stop sharing your entire screen. Share. Is it visible now? I'm sorry, I
Yes,
was
yes.
here.
Now it is visible. Yeah.
Okay, so um, I was introducing Leibniz law. So Leibniz law is made up of two components: identity of indiscernibles and the indiscernibility of identity. So identity of indiscernible means if two objects are indiscernible, which means that for all shared properties F, all detectable shared properties F, if these two things they have the same properties for all such properties, then these two things are identical, okay, up to all relevant purposes. And indiscernibility of identical means if two things are identical, then all their shared properties will be the same. Okay, basically all properties. The shared part is truncating. That is not necessary. And it is commonly believed that proofs of contextuality show that quantum theory violates identity of indiscernibles. But it is not so. Quantum theory satisfies the Leibniz law, ba- basically both identity of indiscernibles and indiscernibility of identicals. And to show this, we think about any two quantum states. If two quantum states are equal, that means all their entries in some matrix representation are equal, then there exists no POVM element that can distinguish between these two states. And similarly, if these two things cannot be distinguished completely, then quantum theory assigns them the same state. So quantum theory does not violate identity of indiscernible nor the indiscernibility of identity. That is one of the reasons why quantum theory is a good looking theory. It is compact because it follows Leibniz law. However, However, quantum theory does violate a derivative of identity of indiscernible. The particular statement is the ontological identity of empirical indiscernible. So, what do we mean by ontological identity? So, generalized non-contextuality, like all other notions of classicality, like Bell's stuff, takes something operational and puts it down to a level of reality with hidden variables. So it says that if there are two operationally equivalent preparations, for instance, they must be represented by the same distribution over hidden variables. Just like in Bell stuff, all no signaling correlations must have a parameter independent ontological basis. Okay, just like that, generalized non-contextuality takes operationally equivalent stuff and assigns them identical ontological counterparts. This principle is called generalized non-contextuality or ontological identity of empirical indiscernibles. If you break the sentence down, the meaning is fairly clear. And just like notions of classicality, this lies between the struggle between operationalists and the realists. So the realists, they assert that there must be a reality, and the operationalists say that we don't care about it. But the notions of classicality connect these two viewpoints on physics, okay? Ontological notions of classicality. And this one's by Robert Speckles. So um, and this principle, the ontological identity of empirical indiscernibles or generalized non-contextuality, is violated by quantum theory. So there is no realist viewpoint of quantum theory that is non-contextual or that follows the ontological identity of empirical indiscernibles. Again, exactly the same as Bell stuff. Like there is no ontological model or hidden variable model of quantum theory that is local causal or parameter independent and out. All right. So before last time we saw how to define Bell scenarios. This time, akin to Bell scenarios, there are contextual scenarios. And in the paper, we introduce a succinct notation to denote any contextuality scenario. So a contextuality scenario is defined as a five tuple. A tuple is a list. So it is this is how our hierarchy is coded as well. So a tuple is a list. It takes into account the settings for the preparation device, the settings for the measurement device, and the maximum number of output of any of the measurement, which can others basically the number of outcomes for each measurement. Okay, so we just have, unlike Bell scenarios, we just have three defining variables: x, y, and k. It's a prepare and measure scenario. So there is a preparation device. It has no classical output, a measurement device, and an output. Okay, and as a result of contextuality experiments, we get just like the Bell behavior, the correlation vector PABXY, we get a vector of probabilities. We, on probabilities which specify what is the probability of obtaining an outcome K when preparation X was prepared and was measured using the measurement indexed by Y. Okay. The other two things specify the details of the contextuality scenarios, which is basically operational equivalence relations. So two things are operationally equivalent if two preparations are operationally equivalent if there is no measurement that can distinguish between them. Similarly, two measurements are operationally equivalent if there are no states that could distinguish them. So operational equivalence conditions specify what uh, um, what parts or what combinations of preparations have to be equivalent to other combinations of preparation, and similarly operational equivalence for measurements or effects does the same thing for measurements. We'll be focusing today just on preparation equivalence part because it's super easy to code. And nevertheless, as an example of a contextuality scenario, um, um, and operational equivalences of preparations, we can think of such operational equivalence of preparations and such operational equivalence for measurement. And the examples given here are a quantum realization, which is actually optimal. And um, and you can check quickly that these states and measurements satisfy these conditions. For instance, P0 plus P1 by half is identity by 2, so is P4 by P5, which is identity by 2, and P2 plus P3 by half is also identity by 2. So the preparation equivalences are satisfied, and similarly, the measurement equivalences, one can easily verify that they are satisfied because the measurements are placed like this. Okay, and there is completeness relation. So, all right. So the attempt of this paper was to give a perception that contextuality scenario perception that was developed with in discussions at CHIP, uh, that contextuality scenarios are exactly like, or to a very large extent, almost similar to Bell scenarios. Okay, so the paper has been written to draw, in a way, to draw relationship between Bell scenarios and contextuality scenarios. It's basically we've tried to mathematically code in the paper, not on MATLAB, in the paper these equivalents. What we saw on our boards and what we saw on our notebooks, we tried to put it out there as easy as and make it as easy as possible. So in the paper, uh, the scenarios are clearly defined. I've already talked about them. Just like the Bell scenarios, the no signaling polytope is has its brother in the contextuality side or sister as the contextuality polytope. So these are both defined by linear constraints on the observed probabilities. Okay, So they form a polytope with finite number of extremal points, and they then yield SDPs to calculate bounds over this space or check the membership of not SDPs, LPs in both cases. Quantum set in both cases we show in a proposition is a convex set, just like the Bell scenario. And the local real polytope is replaced by a non-contextual polytope. Just everything is the same in both cases. And similar to Bell inequalities, we have contextuality inequalities, which are typically, if they are good contextuality inequalities, then they are facets of the non-contextual polytope. However, we found out that in some circumstances, under some peculiar operational equivalence condition, the quantum set, unlike the quantum set in the Bell scenario, where you can realize any correlation by pure states and projective measurement, the quantum set is not so. You really require, for certain contextuality scenarios, mixed states and unsharp measurements, which are POVMs. You cannot have Neymar dilation working in contextuality scenarios. So we prove this thesis using the help of SDPs in this work. We say that we basically show that if you are only allowed to use pure states for each x, px is a pure state in quantum theory, then the corresponding set of correlation is strictly contained inside the quantum set of correlation. And similarly, if you are restricted to projective measurements, you cannot realize the set of all contextual behaviors. This is the main difference, and this is the main problem to formulate a problem in the way of formulating an SDP hierarchy for quantum behaviors in contextuality scenarios. All right. Um, okay. This is to be contrasted with the Bell scenario, where the quantum set, because of Nearmark dilation, can always be realized by projective measurement on or for each local party, and a pure state, pure entangled state shared. But this is just not the case for contextuality scenarios. And to prove this, we used SDP hierarchies. Maybe we can touch, or maybe we can see how to prove this today.
Anubhav,
Yes.
can you please go back to your previous slide? Yes. So this schematic diagram tells us that there are even non-contextual correlations which cannot be produced by pure states and projective measurements.
Yes,
What
and
are these?
this exactly this discovery is still in my Gmail, and this was sent to me by Devlata back when we started out discussing about it. It is true. This is true. The contextuality scenarios are such that stochastic classical stuff, stochastic hidden variable stuff, can outperform
Correct.
pure quantum stuff.
Okay.
You're
Okay.
right. That's a keen observation. So, all right. Okay. And so I will go through this stuff quickly. If two things are operationally equivalent, then for any effect in the theory, effect is an outcome for a specific measurement. So it's just the operator or the mathematical object that represents the outcome of any measurement. For all such operators, which are POVMs in quantum theory, the probability over the two equivalent preparation is the same for all effects in the theory. This means that they are operationally equivalent, which means, see, there is no way to distinguish them based only on statistics. Right? That's where the word operational comes. Similarly, two effects are operationally equivalent if all states supply the same probability to them. Okay, they yield the same probability with this effect. So that's why how two effects are equal. Okay, so uh, okay, excuse me, just a second. I'll do that. in general, in general, if contextuality scenarios with preparation equivalence on the left side um, uh, can have preparation equivalence between a convex combination of the experimental preparations with a different convex combination of the experimental preparation. To handle these property, we introduce another preparation, Q, which is a hypothetical preparation. It does not feature in the experiment. It is just there to handle the operational equivalences well. Okay, so each any single operational equivalence is of this form. You have an hypothetical preparation, and you have its two different decompositions, which are the context in terms of the experimental preparations. Okay, this is how each operational equivalence of preparation will look like in a contextuality scenario. In general, you can have total V different hypothetical preparations, and each having capital V subscript small v different decompositions, and they could be equal. So this is the most general way of writing operational equivalences. Similarly, for measurements, you can have W, capital W, different hypothetical effects, and capital W underscore small w, different decompositions that are equivalent. All right. For each hypothetical effect, you will have this number of if you have this number of different decompositions that are operationally okay. The way the paper is coded, I'm repeating myself because mathematicians are writing the paper with me, so they coded it. The way it's coded, it is we just write these equivalences and we take them to different levels. First, we write them on the level of probabilities, then on the level of quantum stuff, then on the level of classical stuff, and then on the level of moment matrices at the end, which will yield the hierarchy that we work. So just the form of these operational equivalences is required. So I'll go over them once again so that everybody is up to speed. Just a second. All right. Here. Um, and a single operational equivalence of or non-trivial operational equivalence in a contextuality scenario entails a hypothetical preparation corresponding to that equivalence and two distinct convex decompositions of the hypothetical preparation, this and this, marked by different convex coefficient in terms of the experimental preparations x. Okay, this is one operational equivalence. In general, there could be several operational equivalences, each related to a hypothetical preparation qv, and uh, this number or v underscore v number of different decompositions of qv. Okay, if you guys can think of a more general contextuality scenario, there is equivalently general stuff. Please let me know. Otherwise, we think that this is the most general stuff. We can even prove it to a large extent. Similarly, for measurement, we can have W different operational equivalences of measurement, each having QW or each having an effect KW, NW as the hypothetical effect corresponding to each operational equivalence, and J different decomposition in terms of the experimental effects, KMY. Okay, and these are the convex coefficients or of the decomposition. Just the structure of this has to be kept in mind to read the paper. It's written, if you have the structure in mind, you can derive the constraints for the classical set and everything else. We'll see how. But before we begin, uh, we must also keep in mind the Bell scenario. The first thing we see in the Bell scenario is the no signaling polygon. It's a prerequisite of whatever theory you are using to make your resources in the Bell experiment. Every probability distribution that comes out in a Bell experiment must, irrespective of what theory it is, must follow the no signaling constraint. Similarly, in contextuality scenarios, because of operational equivalences, you have some constraints on the level of probabilities. And how do we get these constraints? We just replace the for the preparation side. We just replace the preparation by effective preparation on the probability level. But now the probabilities cannot be decomposed into preparations and measurements, so we just have the probability. So we just replace px here by pk given xy, which are the probabilities in the experiment. Okay, and then we get then we get linear constraints on probabilities because of preparation. And same thing applies to the measurement. We just replace the measurement with um, we just replace the measurement effect by the probabilities. Okay, just the measurements have been substituted. That's all. Again, these are linear constraints on probabilities. So if there are linear constraint probabilities, which is a real vector, positive real vector with some completeness condition, the set of possible distribution forms a polytope. Okay, and characterizing a polytope is a linear program. Super easy to solve, just like the no signaling polytope. Is everybody okay with this part? Is anybody coming along? Are there
Yes,
questions?
Anubhav.
Yes.
Can you just go over equation 4 and 5 a bit?
Yes, of course. See, in at the level of probability, strictly operational level, you do not know whether the theory is a GPT or a GIT or a GOT. Well, informational theory or operational theory. All you have is probabilities. Okay.
Right.
Okay. So what did we have before? For a given preparation equivalence, operational equivalence of preparations, you had a hypothetical preparation Q, uh, uh, which had J different. I think which had
Right.
yes, it had J different decompositions. Okay, so what should be on the level of probabilities? Just because you do not have any object for preparations at the level of probabilities, you just replace the preparations by the probability itself. Okay. So here you say that eh, the effective probability of the preparations of different decompositions of QB must be the same. So this is a number here, and these are numbers. They are
What
replaced.
are x and y here?
X and y are settings of X is the setting of the preparation device, and Y is the setting of the measurement device.
Ah,
Right?
okay.
Is it cool?
Hmm.
Do you get the perception what I'm trying to say here? Because there is no other object here. You just have list of probabilities, and
So
all you can do. Yes,
x and y can be means since these are measurements,
yes.
these need not be
No, no.
means
X is the preparation index, and Y is the measurement index. Y and K.
okay, okay.
So it just basically means for the measurements in your contextuality experiment, okay, you must not be able to distinguish between operationally equivalent preparations just on the level of probability. Just on the if you have one contextuality experiment, you have one set of probabilities. Those probabilities should clearly, just looking at those probabilities, you shouldn't be able to distinguish operationally equivalent preparations. This is what this constraint number 4 says.
All
And the
right, all
same
right.
for measurement. Do you
So
get the point? Please go ahead. Is
yes.
there? Yes.
Uh, so this 4 and 5, the statements are like the same Leibniz identity of indiscernibles in terms of the probabilities, like
Exactly.
observable
Exactly.
parameters. Okay.
Exactly. Yes. It's the same thing. From Leibniz identity of indiscernible, not ontological identity of empirical indiscernible. The
No,
Leibniz
no.
law
Yes. Yes.
will be
Yes.
preserved on all levels. All
Yes.
theories
Yes.
are. This is also a dig at Speckins because he used to write that quantum theory violates Leibniz law. It's not true. They have changed it at the moment. But quantum theory, like any other theory, like classical theory, ontological model, or the probabilistic theory, all follow the Leibniz law. They have to, otherwise they can't be a system of thought. Anyways, but uh, again, you have just like you have no signaling bounds on CSSH equal less than equal to 4 for any no signaling distribution. You have contextuality inequalities like that, and these bounds are computable by linear programs. All right. Now we go to the classical level or the local thing that is akin to local real level. So again, this is, which is called non-contextual. Classical in contextuality scenario is called non-contextual stuff. Here, just like the Bell scenario, like no signaling stuff must have local real explanation. Operationally equivalent stuff must have non-contextual explanation, which is basically identical ontological explanations. So we start out with a measurable space, just like in the previous lecture. A measurable space, we do not restrict the space of our hidden variables because, well, they are hidden, and that is why. And for each preparation, an ontological model associates a probability distribution over the measurable space. It is exactly the same thing what statistical mechanics in classical theory does. It has an measurable space, which is our generalized coordinates, q and p, position and momentum, and each physical system or each stochastic physical system can be described by a probability distribution over the phase space. But now the phase space is not just composed of position and momenta, it can be arbitrary. We just require it to be measurable so that we can define probability distributions over it and take unions and stuff. That's all. It might be anything. And the measurements are just if you find out this classical state of the system lambda or the hidden variable of the lambda, what is the probability of giving the outcome k? This is how effects are modeled on the ontological level. So the operational probabilities, they can be the operational probabilities can be we can get operational probabilities by summing over our ignorance of the particular state in which the system is in. Okay, so that is what we do. We average the effect over the probability distribution on our hidden variable. All right, and this is how we get probabilities. This is exactly the same thing, or it is equivalent to the same thing as Bell stuff. So there you have two effects instead of this epistemic state here. Anyways, to sum it up, we do not have to do anything about non-contextuality today. Just to sum it up, two operationally equivalent preparations must have the same probability distribution over the hidden variable space. This is non-contextuality. Two operationally equivalent effects must have the same response functions underlying them. All right. Um, David Schmidt with Ellie Wolf and Robert Speckens characterized the non-contextual set before us, and just like local causal, uh, uh, just like the local causal polytope, they showed that non-contextual stuff always forms a non-contextual stuff always forms a polytope, and this polytope has a difficulty that as you go up the number of settings, and for Alice and Bob, you get the complexity of characterizing this polytope, even though it's a linear program, explodes exponentially. So to solve this issue, Devada has a way of relaxing the constraints on the non-contextual polytope, which we are exploring on the side these days. But in this paper, they showed that for any contextuality scenario, it's a polytope. Okay, and especially for the contextuality scenario that I gave as an example earlier, they showed that the success probability of or the non-contextual inequality is of this form: some linear functional of probability is less than equal to 2.5. Okay. Um, they gave a linear program description. Even the program is available if you write to LE. We'll give you programs for non-contextual set, but it's still a linear program, so easy. Even though our computers might take a while, coding this is extremely easy. Okay. So it has, if you recall, this scenario has some preparation equivalences that translate into equalities between sums of epistemic states. Similarly, operational equivalence of effects translate to equalities between sums of response names, which are measurements, classical measurements. You can think of the epistemic states as encoding schemes and the effects as decoding functions, or the response functions as decoding functions. But nevertheless, again, this is not important. You don't need to recall. Just the fact that everything is a semantic extension, everything follows the Leibniz law at all levels. So, again, to recall, we start out with a general operational equivalence for preparation, then on the level of probabilities, and now just replace the preparations by classical preparation or the hidden variable or the ontological preparation, which are probability distributions over lambda. We just replace the preparation by the probability distributions of lambda, and we get the operational equivalence that for preparation. And the same thing applies for the measurements. Okay, and in the paper also you will find such a level of coding, so you can it's easily readable because all you're doing is replacing preparation with probabilities, then you get the contextual polytope, and then you replace preparations with probability distributions for that preparations, and you get the non-contextual polytope. All right. Similarly for effects, nothing, just the effect in the classical theory is plugged in there. Okay. Now we must talk about quantum sets, because that is what our tutorial is about, characterizing the quantum set of behavior. Okay, so again, just like in Bell scenarios, how do you say that a distribution is a quantum distribution? You have to find the state and the measurements that reproduce the distribution. And it's a tough task because in Bell scenario there is no constraint on dimensions. Similarly, in contextuality scenario, the dimension of the Hilbert space remains unconstrained. Okay, so it makes the task very difficult. Apart from this, even though it's a semi-definite program characterizing the quantum set, it's not your usual semi-definite program because the objective function is not linear. It has terms of it. Well, it is composed of linear functionals of probabilities that have two semi-definite variables multiplying with each other. So both of these are semi-definite, they have linear constraint, but the objective function is non-linear in the semi-definite. Okay, so it's super hard to characterize, just like Bell scenarios. And if you can come up with a new way of thinking about it, not SDP hierarchies, I'll be very happy and keen to hear that. Nevertheless, the operational equivalences, the operational equivalences then translate to the quantum level. Following the Leibniz law, you just replace each of the preparations by quantum density operators. Okay, and you get operational equivalences of preparations for quantum state. And similarly, you can replace each generalized effect with quantum POVM elements. So these are positive decompositions of identity. E0 plus E01 sum up to identity, and they're positive. Okay, and they're semi-definite variables. It just like it's exactly the same as Bell scenarios, but as we'll see, there are some key differences. We assume that the particular dimension of the Hilbert space is unbounded, but our stuff we can only show at the moment can work on finite dimension Hilbert spaces. I am sure that it extends to infinite dimension, but it's a matter of interest. I'm not interested in infinite dimensional Hilbert spaces. Only yesterday I looked at I332, but nevertheless. Again, semantic extension. Just replace in your most general way of writing your operation equivalences, just replace the preparations by quantum states and the effect by POVM elements. Okay. We prove in our first, we have now for the quantum set, because that's what we are most interested in, we have 7 observations. Okay, things we can prove that are either same as the Bell scenario or they're contrasting with the Bell scenarios. Okay, so first thing that we show is that the quantum set of behaviors is still a convex set. Okay, just like the Bell scenarios. The proof is the same for both. You take direct sums of two different quantum distributions, and you can show that the convex combination of these two things will still be in the quantum set. Okay, but again, finding out maximum violations or maximum values of non-contextuality inequalities, the quantum maximum value, has no efficient characterization because of the reasons that I told you about: non-linearity of the objective function and unbounded dimension of the Hilbert space. Okay. Next, we define two subsets of quantum set where each experimental preparation is a pure state. We call it Q psi, this one, the one with the heart. Why is it a heart? Because we couldn't show that this is convex. Okay, we tried very hard and then we settled with the statement that we are just monkeys, so we can't do everything. Anyways, but um, and so the heart is neither we don't know what the heart is. It's concave at points, and so we are not sure whether it's convex. And the other set is letting our effects be only projectors. So they have the orthogonality constraint, which is, and along with the orthogonality constraint, they have the POV constraint. And we can show that this set is convex. Apart from this, um, apart from this, we show in the rest of the observations that Q psi is strictly contained in the convex set of quantum correlations, which means that there are contextual quantum behaviors that cannot be reproduced by pure quantum states. Okay, and similarly, there are quantum contextual behaviors which cannot be reproduced by projective measurement. And this might not appear shocking to you now, maybe because of the way I'm saying it, but in general, we think about density operators and unsharp measurement as less resourceful than pure states and projective measurement. But in contextuality scenarios, you can get more contextuality with these things. Also, this paves the way of certifying purity of the state or unsharpness of the measurement using contextuality inequalities. Okay,
Yeah, Anubhav, I
and
have a small query. So,
please go.
so the intersection between these two set, that will be assuming pure state and projective measurements.
Yes,
And like, did you try to prove whether that set is convex or not?
we can't prove. We can't prove because of Demark dilation, we can always take projective measurements for preparation or scenarios with just preparation equivalences. So we couldn't prove anything whether that's a convex set or not. But it might be easy or difficult to show because this q pi is the scenarios where we test q psi like parity oblivious multiplexing. They do not require this assumption comes as gratis or it comes as free assumption in those scenarios because of Neymar dilation. And even in those scenarios, we were not able to prove that q psi is there. So in the intersection, it's already in the intersection. But we should look at it at some point. We made some progress, but it was very difficult. Maybe it is not convex. That is my feeling. That q psi and q psi pi, which is the intersection, they are not convex. But we will see. They are convex when you have these contextuality scenarios which are equivalent to Bell scenarios. Of course, they are convex there, but not in general. Is it okay? Does it answer the question?
Yeah. Yes. Yes.
Okay. All right. So this is the summary of the seven observations that follow in the paper. There are two more that I missed, which was whenever there is less than three preparations, less than equal to three preparations, everything, including the contextual polytope, is simulable by non-contextual models. Okay, so there is no violation of non-contextuality when you have less than three preparations. This has a very nice proof in terms of which follows the fact that generalized non-contextuality is equivalent to simplex embeddability, and three preparations can always any probability distributions over three preparation can always be embedded in a simplex, which is the triangle, and that's why you do not get any. We can discuss this later. Again, for and a for scenarios which do not have any non-trivial preparation equivalence, we get the same effect. There is no contextual behaviors. Everything is simulable by non-contextuality. This gives me and some of my friends the perception that preparations are of more significance than measurement when it comes to ontological notions of classicality, especially of the kind of contextual. Okay. The fifth observation is that if you have no non-trivial equivalences of measurement effect, then because of Nearmark dilation, you can treat all of your measurements to be projected. Okay, so we can use the projective assumption in such cases. All right. So now the challenge is to come up with a hierarchy that applies to any contextuality scenario with preparations and measurement and even transformation. We are working on that simultaneously. But come up with an SDP hierarchy that will bound the correlations, quantum correlations in any contextuality scenario. Okay, and the main challenge with that is the two observations. One, that we cannot take pure state as assumption, and the second thing, we cannot take the projectors to be to the measurement effects to be projectors. Which, if you recall, in the last lecture, they give this nice looking structure to NPA hierarchy that the top row is equal to the diagonal row of the moment matrix. But now it is not true. Okay, and we one can show that this is crucial to the convergence of NPA hierarchy. If you remove this, NPA hierarchy is as good as the no signaling constraint. Okay, so we have to now think out of the box to come up with a new hierarchy. That is one, it's easily implementable, like everybody can implement it in say a tutorial session like I demonstrate today. Second, it is a valid hierarchy. Okay, so it should not take either of these two assumptions. The first one is also an assumption in Bell stuff. Okay, let's see how we deal with these two assumptions. And the first way, the algorithm to go about it, the first way is to use the fact that for any list of operators, a moment matrix hinged on the semi-definite positive and bounded trace density operator must be positive semi-definite. To each preparation in our experiment, we associate a moment matrix which is hinged on the particular quantum state. And then one can show, and it's fairly easy because this from the gram matrix for the state rho x, this moment matrix is just the gram matrix, that this is always positive semi-definite for each state. So we have now, in Bell scenarios, we had just one state, so we had one moment matrix. Now we have capital X different preparations, so we have capital X different moment matrices. All right. And for now, we are looking at no non-trivial measurement equivalences. So everything is projection simulable. So our operator list, just like the last lecture, the operator list will be formed of projectors of Bob, for instance. Okay, and then we'll have our usual constraints, which is okay. If so, maybe not. Okay, this is for general contextuality scenarios, so there might be measurement equivalences. Then we have, as you can see, these correspond to probabilities of observing an outcome 0 when measurement 0 was performed on the preparation X. Okay, and this is the probability of obtaining 0 when measurement 1 was performed on preparation X. Similarly, this. However, the diagonal things, now we do not know what these things are, because if these are unsharp effects, this would strictly be majorized by E00. And in case these are projectors, this would be equal, but we cannot assume projectors. So these things remain basically unconstrained in our implementation. And this is a big problem. Okay? So first, we must resolve the problem of not taking pure states. Okay? The way to resolve the problem is in the Leibniz law, which is first we go from as you know that we have gone from the operational equivalence level to the level of probabilities, then to the level of classical stuff, then to the level of quantum stuff, and now we can go to the level of a semi-definite hierarchy and replace each preparation by a moment matrix. This follows from the fact that the moment matrix is a linear functional of the state. All right. So we can just replace the state by moment matrices. If the states are operationally equivalent, then the moment matrices will have these equalities. Just because the moment matrix is a linear functional of the state, right? And so you can replace the preparation here to get the operational equivalence of among the moment matrices. So this is how we resolve the fact that we cannot take pure states as our preparations. Okay, because now the moment matrix is just is positive semi-definite if it is hinged at a density operator. It does not care what states are. Also, in this formulation, we get operational equivalences directly from the contextuality scenario. We do not care what is actually inside the moment matrices or what operators index moment matrices. They just need to be linear operators. But these constraints are on the level of the moment matrices, not on the level of the contents on the moment matrices. Okay. So this is how we encode our operational equivalences on preparations. All right, is everybody clear? Because this is how we code in like few minutes.
Anubhav, what is this O index for the moment matrix in the decomposition?
This is the hypothetical moment matrix that corresponds to QB.
Yes, yes, that I understand. But for each
Oh,
element
this one.
of gamma x, yeah. So this involves like for different layers of this.
No, no. Yeah, this is for some operator list code. So
Yes, so it can be for the first layer it will be O1 and the second
yes,
layer it will be O2 and so.
yes, yes. For the first layer, see for the three binary outcome measurement, we had this. The second level is defined as all two strings of
Right,
this,
right, right. Okay,
and so
okay.
on and so forth.
Yes, yes.
So the same concepts.
Right.
Um, okay. Okay. Similarly, we can encode inside each moment matrix measurement or measurement equivalences, I guess. Okay, but you have to encode it inside the moment matrix because of the formalism. There is a possibility of doing it, but because we cannot assume projectors in generalized contextuality scenarios, this implementation is very bad. It is actually as bad as, it is actually equivalent to the linear programs for contextual polynomials because things cannot be constrained. All right, so we have to resolve this issue. And for this, we had to come up with an entirely new way of thinking about hierarchy, of SDP hierarchies. This has never been done before, and this is, in my opinion, the most exciting contribution of the paper. For any identity bounded positive semi definite operator, you can parameterize in terms of arbitrary dimension. You can parameterize it as identity over 2 plus some unitary operator u plus some unitary, the dagger of that or the complex conjugate of that operator divided by 4. You can always do this. The way to see this, think about this positive semi-definite, identity bounded positive semi-definite operator in its diagonal basis. You will have some positive values which can at most be 1 in the diagonal basis. In the diagonal basis, this would have complex e to the power I phi eigenvalues, and this would have the complex conjugate of that. So if you add those two together, you get the real part. But the real part is bounded between 1 and minus 1. So you shift it by, you divide it by, or I think 2, and then you shift it by a half to get it to be positive. Okay, so you can do this for any positive semi-definite operators. This gives a new way of thinking about quantum theory. Last time we thought of quantum theory as a theory of semi-definite operators. Now we can think of quantum theory as completely unitary explanations based on theory of unitary operators, because you can reproduce density operators, unsharp measurements, sharp measurements, pure states, or even transformations by single unitaries. Okay? This resolves our problem that the diagonal values. If we take an operator list now corresponding, so for each effect you'll have one uniter, okay, and the operator list now will correspond to these uniter. Okay, so the unitaries will index our moment matrices for each x, for each state. There will be some unitaries indexing the moment matrices. Okay, and if it is so, then the diagonal values will all be unity, because you'll have u dagger here and u here, and u dagger is identical. So the diagonal values can now be bounded. Okay, this hierarchy performs stupendously well. This is crazy. We had a competition for the same paper with Armin, and their hierarchy has to go to level 7, level 8 to retrieve tight upper bounds, while we can do it just at the first level, right? So this is just plain out of the box amazing trick. I'm still working about this, and I'd like to discuss what could be implications of this parameterization. There are some cool ways of looking at this, maybe. But we are basically familiar with this. This is just for density operators. This is identity plus n sigma by 2, the Bloch representation. It's not something clearly out. But this gives us a way to bound um, the diagonal values, and the probabilities can, because of this linear thing, the probabilities can always be computed from the moment matrix like this. We don't need to go about this because today we are not looking at matching equivalences, but just to inform you guys. But nevertheless, today we'll be focusing on something that Devada has done a lot and everybody in our group does a lot. Basically, it's the RAG group with Marcin here, the random access code. Okay, and especially one version of the random access code which is called parity oblivious random access code. These are my, if CSSH is my favorite linear functional of probabilities in Bell scenarios, the 2 to 1 random access code which is equivalent to CSSH is my favorite uh, uh, non-contextuality. Okay, in a random access code, Alice gets a string of bits, preferably and for now uniformly distributed. Okay, so she gets two numbers, 0, 0, 0, 1, 1, 0, 1, and she has to encode in each round. She gets a pair, say 0, 0. She has to encode it onto the preparations, onto a preparation which is indexed by the input of Alice, and send it to Bob. Okay, Bob then measures this state using a choice of measurement which is again binary, and outputs a binary output. Okay, and the task is to maximize the success probability of guessing the yth bit of Alice. So suppose Bob gets a 0, then we'd like to maximize the probability of Bob guessing the 0th bit of Alice, which is x0. Okay, and similarly, when Bob gets a 1, she has to he has to guess the first bit of Alice, which is x, right? Or the second, zero. Anyways, but this is the parity oblivious line. The success probability is a linear function of probabilities, as it should be, because this forms a facet of the simplest contextuality scenario. Um, is just the total success probability of obtaining yth bit of Alice, given Alice had a x as input and y as Bob's setting was y. Okay, and we normalize this by 8 because these things are uniformly distributed. Then we have 8. Okay, and parity oblivious constraint. So this is the rack structure. This is independent of contextuality. You can put the dimension constraint and self-test MUBs or whatnot. But here the constraints are, there is no constraint on dimension. The only constraint here is that no information about the parity should be. So if you think about it once, what is the parity? The parity is basically XOR of the first bit with the second. Okay, so you are mapping two bits to one. Okay, so the XOR of P00, XOR of 00 is 0, and the XOR of 1 is 0 as well. So the effective preparation for parity 0 is given by this, and the effective preparation of parity second is given by this. To ensure parity obliviousness, you must have this equivalence constraint, operational equivalence constraint. Okay. This means that what do you recall what operational equivalences are? There exists no measurement in the theory that can distinguish these two preparations. If you cannot distinguish the two effective preparations for two different values of the parity, you cannot find out what the parity is. So it is necessary and sufficient for parity obliviousness to hold that these two parity preparations must be operationally equivalent. Okay. Under these constraints, one can easily show that the success probability of the rack is bounded by three quarters. Okay. However, we know from previous works by Manik and I think as far back as 2017, it was that the maximum, and Manik and even Speckens, that the maximum success probability of rack for quantum things is the Sirelson bound, is exactly the same as the quantum Sirelson bound. In CSSH, it's half 1 plus 1 by root, right? This is what we'll code today, the parity of previous random access code. So if you have any questions, please ask about this scenario now. Is everybody up to speed? Hello? Hello? Is it okay? Okay.
Yeah, yes.
Okay. Okay. So maybe we could quote some part of this, but so first thing what we did is we changed the operational equivalences by introducing a parameter alpha on the right hand side instead of a half. We have a parameter alpha, and then this is basically used to show that q psi is contained always in q. Because there is no operational equivalence of measurements, we can always take projective measurements. So this is the right hierarchy. And then we can show that for some cases, the success probability, for some operational equivalences, the success probability, the maximum success probability for pure states, which is bounded by Q1 psi, is strictly less than even the non-contextual bound or the contextual certainty. So this proves our thesis that Q psi is completely inside the quantum set. So we achieve this by twisting the operational equivalence in such a way that it's just not feasible for pure states to be there. All right. Um, and we tested out a lot of non-contextuality inequalities using the unitary parameters, and we showed that the the hierarchy performs extremely well and it can recover quick bounds. Okay. Well, I'm not going to go into details. And when you have an SDP hierarchy, you can get key rates out of it or certify randomness out of it. And to showcase the application of all of this, we devised a SDI protocol based on 3 to 1 rack, which is not equivalent, 3 to 1 parity of previous rack, which is not equivalent to any Bell scenario. And we showed that Alice and Bob can distill secret key for very high success probability of well, but they can still distill a secret. Anyways, but before I go to the coding section, I'd like to quickly talk about foundational implications of this. For me, the fact that pure states and projective measurements are not enough to reproduce all contextual behaviors um, was the biggest finding of this. And in my foundational notebook, this go as this leaves a perception which I talked about. Basically, this means that in a contextuality experiment, the experimenter himself cannot have the knowledge of the convex decomposition because if they do the success probability, because the experimenter is honestly experimenting, the success probability will come down to the pure state or the unsharp measure. Okay, so this, from the point of view of experimenter, nobody should be able to know the convex decomposition. Otherwise, there is no violation of contextual. Okay. This requires, say, the mixed states to be prepared as subsystems of maximally entangled state, for instance. Okay. So this gives me the importance of the ensemble viewpoint of quantum theory, which is the ensemble is of relevance. Okay. This is succinctly was told to me at the Oliva station on a notebook by Devada earlier. This was his idea, and this gives a new kind of interpretation of quantum theory now, which is backed by semi-definite programming evidence. That so we are always questioning whether the wave function is real. I think contextuality experiment shows that no, maybe the wave function is real is not the real way, good way of thinking about it. You don't get a proper classical structure, but the density operator is real. So if you zoom into an atom beyond the Planck's length, you'll see the density operator written there, rho, instead of psi. Okay. Today is not a foundational talk, so I won't spend a lot of time. But I claim that this is also the computational interpretation of quantum theory, because this is how my computer stores the quantum states on its memory. Okay? And such an interpretation, row complete interpretation of quantum theory, is completely non-contextual. It doesn't violate contextuality, and the reason for this is okay. Reason for this is very simple. Let's see the psiontic interpretation of quantum theory. This diagram is again from Weber's notebook. Um, to each, say we have four preparations, 0, 1, and plus minus. Okay? And they have such distributions. This is basically Dirac deltas over an ontic state corresponds to directly the Hilbert space, okay, and vectors on the Hilbert space. So if we mix two preparations, say 0 and 1, we get a different distribution as compared to when we mix plus and minus. Alright? This is contextuality. This means that this classical model of quantum theory is contextual. Because even though I cannot distinguish on the operation level identity by two from identity by two, on the level of reality in such models, these two distributions are completely distinct, which are by the red shaded part and the blue shaded part. Okay, but if you take the row complete interpretation, this means each ontic state is one-to-one reference with the density operator itself. So once we have prepared identity by two, there is a separate density operator for identity by two. It does not really preserve the convex mixing here on the ontic level. It gives a separate density operator. So there is no contextual, because the same thing represents same things which are similar on the operational level. Okay? Is it okay? Is it okay? A good description, Devana? Maybe you'd like to say a few words, or is it okay?
Yeah, yeah, it's fine.
Okay. So
Yeah,
this is one
it's
of
very nice. Maybe you might want to say then why this the row complete model is also violates the inequality, or let's say it violates the non-contextual inequality. Like what assumption it violates? It might be.
it violates preservation of convex coefficient. So
Yeah. So
convex mixing on the
overall, it might sounds like inconsistent, because we are giving, like Anubhav is telling, a model like lambda, which is non-contextual, but it also reproduce all quantum predictions. But it is not inconsistent because yeah.
yeah, because you see, like there is a hidden assumption in non-contextuality, which is operational preservation of convex mixing. Okay, I don't have a good acronym for that. So this is what is violated in the row complete model, and you can preserve non-contextual, okay, or ontological identity of empirical data. Nevertheless, however, we have a better notion of classicality that. So basically, you have a model, ontological model of quantum theory, which is completely non-contextual. Okay, so there is a way of looking at reality of quantum theory that is completely non-contextual. But then we have a notion of classicality for which we have an SDP hierarchy as well, that just which is called bounded, where we have a bad name for it, we are changing the name at the moment, but that thing can be that thing does not have these extra assumptions, like hidden assumptions like OOP is here. So any model of quantum theory, be it rho-ontic, be it psi-ontic, everything violates that notion of classicality. Okay? It's not too strict. It applies up for three preparations where non-contextuality cannot see, and it's simply better. Okay, I'm not going. I do not have the liberty to go into it at the moment, but check it out. And I did this with Vicky and Matev, which are very close friends, and we had a lot of fun doing this project. We actually did this in 7 days, because Armin told us that he'll upload the paper in 7 days. So we did it in 7 days, sleepless nights, but awesome fun. And that's it. Is if are there questions before we move down to the coding part? We'll be coding about 2 to 1 parity of radius. That okay? Is everybody ready to code? Come on, people! Somebody. I hope I was slow enough to give you the perception of the word. This is not the
Yeah, okay, yes.
okay. Um, um, all right. So just a second. MATLAB's taking too much time. My computer is acting weird. Okay, people, if you have any questions regarding the codes from the last tutorial, please let me know, and we can address them now before I start this one. Okay, no questions again. But okay. So you must come along with me. Now it's an informal tutorial. I'm doing this so that you encode your own contextual scenarios at your own turn. So this must be interactive. I cannot just speak to a machine and code, because then I will just write the code. I will show the demonstration and be off. If that's what you want, I will just send you the code. I have all of them. But if you want to learn how to think about writing a contextual research, interact with the place. What do you need? What do you is the coding way of last time is okay? Tell me.
Anubhav, I have this. So last time you said that when I'm optimizing the subjective function in Q1, then you cannot get the optimized row and the measurements. But you could actually print after the iterations, right? The row, I mean, after these iterations, you can actually print the state and measurements.
Yes,
Right?
yes. In Seesaw,
Even
at all points you have the state and measurement.
not seesaw. I'm talking about Q1 also.
Okay, Q1, no, there is no state and measurement.
Why? I mean,
You can just have the moment matrix, but nothing inside the moment matrix.
yes, 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 yes. No, 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 no. Oh, yes, I was talking about seesaw. Okay, 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 okay. Yes,
Seesaw, because it searches over the states and measurement of a given.
yes, 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 yes.
So today we can, if you guys are up for it, we can do Seesaw for 2 to 2-to-1 parity of previous rack, which is the smallest proof of contextuality, and a Q1 level for 2-to-1 parity of previous rack. That would be simple, and everybody could implement this on their own. I'll send the codes at the end as well. But is this a good plan?
Yes.
All right, okay. This is
Anubhav, can I make a suggestion?
yes, of course.
Yeah. So I missed your last class actually. I saw the recording and I was not aware of your class. So I got your codes and I was going through the documentation and I will learn about all the commands. But if you can, while you are coding today, right now, if you can just point out to the
Mm.
commands like what they do when and with a bit of reference of your earlier class, it would be very helpful
Okay,
actually.
for sure. I will do it quick because there are people who have a lot of work also here. So I will
Yeah,
do
yeah,
it
yeah.
quick. But if you have questions, please write to me. Do you
Yeah,
have
yeah, yeah, sure.
Have
Yeah.
MATLAB?
I have MATLAB. I have installed all the necessary packages, and
MATLAB?
I also
I okay. There are only four. So MATLAB, QVT Lab, YALMIP, and SDPT3.
everything I have. I also have your codes from Devada, and
Yes.
I am going through them. If I have any question, I will surely contact you.
Yes. No problem. Okay. Let's see how
Thank
to.
you.
Uh,
Thank you.
okay. No problem. Absolutely no problem. Okay. So first, we must. What do you want first? The seesaw or Q1? Q1 is easier, more perceptive, does not require states and measurement. So what do you want? Q1 or seesaw first?
As you wish.
Ram, with Ram and Samrat, we introduce extended racks, but with dimension assumption. But Ram and Samrat, if you'd like to work on extended racks and polyparity oblivious constraints and other SD constraint, this would be uh, the right starting point. Okay, all right. So I like Q1 better. So this is what I do. So we start out by writing a function, and you can code with me because I'm talking to you while I'm coding. So you can code with me. And as a result, I want the success probability S rack name and nothing else because this is Q1. So S rack Q1, and it takes us nothing as input because we are writing a simple code. Now we recall that in the presentation, let me show you hierarchy. Just a second. Yes. To each preparation, we associate a moment matrix. So our preparations in the parity oblivious rack case are indexed by 2 bits of input to Alice. All right, x0, x1. All right.
Yeah, এটা একটু শুনুন।
So we'll have four moment matrices, but let us define the size of the moment matrix. In a 2-to-1 rack, there are two measurements, okay? And there is no operational equivalence for measurement, so we can assume them to be projected. Okay? So we don't need the unitary parameterization for this implementation. For the unitary parameterization, I have given a code at the end of my paper on quantum that everybody can implement. Just copy the things and it will work in MATLAB. And for to the 2-to-1 rack, these are projectors. Okay, so for the first measurement, which is denoted by Y, we only need to take into account the first projector. The other projector can be obtained by completeness relation, identity minus this, right? And similarly, for the second measurement, you just need one projector. So how many entries in the moment matrix then? We have just three entries in the moment matrix, okay, which is identity. The operator list corresponds to identity operator, the first projector for the first setting of Bob, and the and the first projector for the first setting for the second setting of Alice. So just three, okay. And how many we have? Gamma 00 is a semi-definite variable, SDP variable. And what is it? It is 3 comma 3. What is a semi-definite variable? It's a Hermitian object. It's also complex. You can take it to be real without lots of generality, but I don't want to prove this at the moment, so I will take it to be quantized. It is computationally inexpensive. Now, similarly, we'll have semi-definite variables for all four moment matrices.